All right. Hey, everybody. Thank you for joining. We have Dr. Karthik Mohan here with us today. He is currently a staff scientist at eBay working on chatbot and LLM applications. He also teaches some AI and ML courses part-time at the University of Washington, Seattle. So I'll hand it over to him and he'll walk us through the best practices of ChatGPT. So please enjoy and add in your questions via Q&A, and we'll review those towards the end of the session. Thank you.
Thank you so much, Casey, for the introduction. Let me share my screen here and we can get started. Right. So I guess I'm sharing my screen. So hi, everyone. I'm Dr. Karthik Mohan. You can just call me Karthik. I will be talking about best practices of using ChatGPT for NLP tasks, and specifically focusing on prompting principles and data labeling, data generation, benchmarking. Actually, more so on the last three than the first one, because I think by now, like a lot of us are familiar with prompting. So I'm not going to spend so much time on that, but I think the use of ChatGPT for data labeling, data generation, benchmarking, and specifically looking at industry use cases, and maybe also looking at use cases at Indeed is something that we will kind of take a look at. So it's a little bit of a misnomer to say best practice of ChatGPT for NLP, because ChatGPT is an NLP engine. But what we mean by that is like customizing the chatbot and the chat interface to suit our business needs in natural language processing. So a bit about me. I did my PhD at UW, and then I worked at Amazon for a bit. And then I worked at Meta, and then I took a break from industry, and I was teaching a lot of AI and machine learning courses at University of Washington here in Seattle. And I thoroughly enjoyed doing that. I taught an LLM course this year as well. And after taking a break, I kind of joined Chewy. And after that, I'm right now a staff scientist at eBay, and I work on LLM applications and pushing LLM models to production for eBay applications. So today's talk, I'll break it down into 4 components. The first is introduction and motivation. The second is like a little bit of engine behind ChatGPT, history of ChatGPT, just kind of refreshing memory, maybe a fresh perspective. If you've already heard a lot of talks on ChatGPT, this might give a little bit of a fresh perspective. And then the meat of the talk is number 3, which is ChatGPT use case for NLP. So we'll dwell a lot here, and then we'll go into a little bit of examples and a notebook demo. So let's get started. Introduction and motivation. So ChatGPT and LLMs, right? They're like a buzzword. They're like water right now. They're getting used everywhere. If you look at this graph, it talks about the amount of time it took for different apps to reach 100 million subscription or users, right? And you can see as you go from Uber to Snapchat towards ChatGPT and Threads, the time keeps reducing. Like ChatGPT just took like 2 months to hit 100 million users after it got released at the end of 2022. And then obviously Threads was even faster. It took 5 days. And if you look at like, this is a little bit old data. This is probably from last year. The total visits in the last 28 days, across a few search engines and chat, OpenAI was like in the order of billions. And so, this just skyrocketed after the release of ChatGPT. And if you look in terms of popularity in papers, this is like the number of papers published in the last 7 days in academic conferences and journals. If you look at the graph before 2022, it's kind of flat. Like you see 1 or 2 papers here and there getting published on this topic of natural language processing. And then GPT-3 happened, and you see the spike in the middle of 2022 just kind of jumped up. And then GPT 3.5 happened, which is ChatGPT. And after that, you see the huge spike that happened in the middle of 2023, because a lot of papers were kind of like thinking and using or ideas related to ChatGPT. And so it's super popular. And this also leads to it being very hard to catch up and stay up to date But Mark here, who's 32 years old, kind of disagrees on that. And the other one is that, I mean, just a little bit of a side note here is that this image is generated by GPT-4. And as you can see, LLMs are not good with generating text within generated images. So this is a generated image, right? But if you see the paper that Mark is reading here, it says generative something AI. So anyway, side note. So beyond the hype, so there's a lot of hype, like everyone's talking about LLMs, ChatGPT, and I think many companies are looking at bringing LLMs or ChatGPT in some way, shape, or form to augment their business needs, get lifts, increase revenue, and hit a lot of business metrics. But where do we really get to use it? Well, this is a kind of a schematic that I took from the web that kind of highlights one of the applications where you have a query, you have a list of documents, maybe resumes, maybe job recs, and then you need to do a search, and then LLM uses the search results to summarize. So there's a search component, and then there is a LLM summarizing generative component. So we have generative AI meets retrieval, and that's what we call RAG, retrieval augmented generation, right? This is one of the examples. But more broadly, right, wherever we have business tasks that require the use of AI or machine learning to mine insights from text queries or text documents, then LLMs have become the state of the art. You cannot beat them, in a very significant way. So you have to use them, you have to modify them, you have to kind of fit it into the stack in some way, shape, or form so that we can get the best results. So today's talk will go into NLP use cases of ChatGPT. So before that, I want to just kind of talk a little bit about the engine behind ChatGPT and also a little bit about the history of ChatGPT, because the history informs the limitations that used to exist and have been fixed, but also the limitations that have come up after ChatGPT has been released, right? So we'll kind of take a look at that. So ChatGPT heavily relies on large language models to power its responses to users. What exactly is a large language model? Firstly, what's a language model? Let's talk about a language model. Then we go to large language model. So language models are scientific, data-driven models that help machines understand language and patterns in sentence construction. How do you construct a sentence? How do you put words together? Where do the verbs and nouns come in? How do you say something that is meaningful? How do you use context? How do you summarize things in a way that sounds human-like? So language models learn this from text available on the web, right? And so as an example, I just got promoted. I'm feeling so blank. What would the blank be? Probably happy, right? You would say, yeah, sure. I think you're feeling happy. So this is one example of next word prediction. So this is one of the tasks that has been there in natural language processing for like decades. People have been working on this. And then it could also be in the middle. So it doesn't have to be at the end. I just checked my application status and it got blank. It's frustrating. What would you guess the blank to be? So you guessed it right. It's rejected, right? So this is like not next word prediction, but random word prediction. You mask certain tokens or words in a sentence and say, can you predict this? So the transformer architecture, which is the basis of ChatGPT, is based on masked language model training. So you mask these words and then you say, can you make a prediction? And then you can get these sentences from different documents, and these documents are mined from the web. So you have a huge repository of data to generate these sentences and then do this masking and then make predictions here. Okay, so we spoke about what a language model is. Let's talk about what a large language model is. Large language models are models that are learned from massive corpus of text. I mean, really, really massive. We'll look at what massive really means here in terms of numbers. And they're known to be very sophisticated in understanding of language and can be generative in nature. And LLMs, it's been found out beyond a certain point with a certain number of parameters, it starts to exhibit surprisingly positive or useful properties in terms of reasoning or logic. It suddenly opens up a whole new dimension once you increase the dimensionality of the model beyond a certain size. Like you'll be talking about billion parameter models or 7 billion or 80 billion, suddenly something gets unlocked, which wouldn't have been unlocked if you only had 100 million parameter model. So there are some surprising benefits of being very large, especially in terms of reasoning and other tasks. And LLMs are also known to be generative in nature, which was missing with respect to earlier AI models that are used for traditional machine learning. We'll talk about what large exactly is in a bit, so we'll cover that. But before that, I want to go into the history of these language models. How did machines work with language before, and how do we do it now? Yeah. So one of the first AI models is called a perceptron. A perceptron is basically an artificial neuron. Like we have like 1 billion neurons in the brain, right? These are real neurons. So the early scientists, they said, can we mimic the real neuron with an artificial neuron and see if it can do some computations and do something useful for us? And so that's how perceptron came about. It's basically you take in a set of inputs, you kind of mix them up and get a result and say, hey, do you think this is right or wrong? So it could just be something like, hey, as an example, if you want to make a prediction on, is this resume a good fit for a particular job, you would extract certain features from the resume, mix it all up with this a summation or some transformation, and then outcomes and output, yes, no, confident, not confident, etc. So we can even use a perceptron, a simple perceptron, for making predictions like this. But there were issues with perceptron, which is like it's limited in nature. It can only do a certain task. So people took a perceptron and chained them into a whole set of layers. And that's what we call a feed-forward neural network. So now we have a bunch of artificial neurons. So we have an ANN, artificial neural network, instead of just a single artificial neuron. So now there's more capacity to do huge transformations and learn. You can look at a cat and a dog and say, is this a cat or a dog? And it'll do a good job on that. But maybe a perceptron was not able to do that. And then came RNNs, which is recurring neural network, which is you take this feed-forward neural network and chain it. So this is like an example of one of the earliest generative AI models. Like we talk about Gen AI, generative AI these days a lot, but one of the earliest generative AI models was RNN, because it was generating one word at a time or one token at a time and doing a really bad job at it. So one of the issues of RNN is it didn't have good memory. For example, if you did next word prediction with RNN, say, I just arrived in New York. In a few days, I would like to visit this city. You wouldn't say New York, right? But RNN would say New York sometimes, and it wouldn't understand that you already are in New York, so you would like to visit a different city. So it had a short-term memory. And to fix that came LSTM, which is long short-term memory network. So that's LSTM. And that did a better job than RNN. So now if you went and asked the same question or same task, I just arrived in New York. In a few days, I would like to visit the city. You probably say Seattle. So I'm from Seattle. We are all from Seattle. So doing a better job there. But this is still not fully generative. LSTMs could generate, but maybe like a couple of sentences. After a while, it would start hallucinating. It might start repeating words. It might start, saying things that are not factual. So these were like one of the earlier Gen AIs where you couldn't really rely on it. You'd kind of laugh at it. You'd say, hey, this doesn't really work. And then came transformers. And as the word says, as the name says, transformers really transformed the way we look at AI. So the graph on the right, that's the really famous, from the really famous paper, Attention is All You Need by Vaswani et al. And it has this encoding and decoding transformer. And it turns out the decoding transformer is the heart of GPT models that are getting used these days. But so it's not that we have discarded transformers in any sense, because transformers are the foundation of large language models. We still get to use transformers for business tasks every day, and we'll see examples of that. So one of the transformer models, which gets used a lot these days in industry, is BERT. It's typically used for like, you might want to classify sentiment. If you're doing review, if you have reviews in some place, reviews data, you want to classify positive, negative, sentiment analysis. Summarization, you want to summarize, maybe you want to summarize a resume, maybe you want to summarize a job description, maybe you want to summarize some other data point. BERT could still do it. It may not do as good a job as ChatGPT would, but it's still capable of doing it. And more importantly, these days, BERT gets used for intent detection, keyword extraction. I want to detect intent here. What's the intent of the user? What is, let's say the user is actually communicating with a chatbot that can understand queries on doing a match, right, with a job rec. So you want to understand what the user is saying. So can you understand the intent? Can you understand what keywords can you extract? So you can do discriminative tasks with BERT, right? So GPT versus BERT, while BERT is purely about encoding, and it's called an encoding transformer, GPT is purely a decoder, and it's called a decoding transformer. So you need a decoding transformer to generate. But people thought you needed an encoding transformer to discriminate and understand. It turns out GPT-3 and GPT 3.5 completely changed the game. They said, we can do away with encoding. Let's just use a decoder. It'll generate, it'll understand, it'll reason, it'll do everything that we need. Let's just go with GPT. And so that's where the innovations brought about by OpenAI, they really pushed the boundaries of what GPT can do with GPT-2, GPT-3, GPT 3.5. And that's how we see it being very useful, is they moved away from encoding transformers to decoding transformers. So GPT-X, where X can be any of these versions, are decoding transformers that are trained to predict the next token given the past, and very good job at it, right? They can generate entire paragraphs that look logical, grammatical, and structured because they've been trained on massive amounts of data. So the ChatGPT framework consists of like a pre-trained large language model with supervised fine-tuning on high-quality data and reinforcement learning with human feedback. So there's layers of fine-tuning, and they all have different models for it, and they all have different data requirements. And when we put it together, we get ChatGPT. Otherwise, we just have GPT, which does an okay job, but you need to fine-tune it, supervise it, add human feedback, do reinforcement learning, and then we get something like ChatGPT. This is a graph that depicts the process. So if you look at the first vertical, that's just pre-trained model on trillion tokens sometimes, and massive data mined from the web, a huge corpus of data. And the second vertical is like supervised fine-tuning, where you fine-tune on high-quality data. So the first one is probably like low-quality data. The second is high-quality data. And then the third is like even more fine-tuning on like, being very precise. If you have a question and you have two answers that are close to each other, is this one better or this one better? So you're training the model to discriminate and pick the better one. Even though you have two good options, you pick the best one. So you're really fine-tuning it to be more precise, and that's reinforcement learning with human feedback. So these three components put together result in ChatGPT, or even, let's say, open models like Llama or DBRX and others. So let's talk about large language models. We briefly mentioned large language models. We said we're going to talk about it. So some of the recent models like Llama 2, Llama 3 have been releasing like really massive models that can understand up to 1 trillion tokens. So here's a question for all of us. 1 trillion tokens requires how many books, right? Any guesses? You can just take a guess. How many books would you need to read to actually generate 1 trillion tokens? So here a token could be a word or a subword. Usually a subword. So you just take a guess. So one book is 50K tokens, right? There's like 50,000-ish words. So that's one book. 1 trillion tokens is 15 million books. So if you think about how much data is large, it's 15 million books worth of data to even generate 1 trillion tokens, right? Maybe even more. And that's the amount of corpus that these large language models actually mine from the web to do pre-training and then fine-tuning and so on. So large is not large, it's massive, it's ginormous, right? 15 million books. Okay, so that's a little bit of a history of large language models. So we started with perceptron, and we went all the way to ChatGPT, and we saw how things have evolved from perceptron to RNNs to LSTMs to transformers to GPT-X to GPT 3.5, and how it all came together. So it's a brief history of this. Okay, So that's part two. We'll go to part three, which is kind of the meat of the talk. We're going to talk about ChatGPT use cases for NLP and specifically for uh, uh, business applications, right? So let's take a look. So this is like a graph taken from a paper that talks about the use cases of Instruct GPT. It's one of the GPT models, instruction fine-tuned. So when you fine-tune it for instruction, it's an Instruct GPT. So the majority of the use cases are like generation, open QA, brainstorming, chat, rewrite, summarization, classification, etc. But if you look at the business use cases that we really care about, it'd be like, I want to have a chat bot where I can chat, right? And more specifically, I want to have a task-oriented chatbot, right? Not just any chatbot. We don't want to ask, how's the weather? How are you doing? Hey, I'm not feeling good. Can you help me out? We don't want a chatbot that answers general questions. We want to be task-specific. Also, classification is another use case. Data annotation and data augmentation are another use case that come up in businesses and in the industry, right? And so we'll see a few examples of these more specific business-oriented use cases of ChatGPT. So let's start with simple prompt engineering. So we can do prompt engineering for information retrieval, like just like one-off prompt engineering. It's very easy to do. So let's take an example of that. So I just like tried this out today. Like this is with GPT 3.5. Give me 10 different keywords I can use to tag resumes that fall under the scope of software engineering. So let's say I want to take resumes in the broad category of software engineering, and not roles, but like keywords, because roles are obvious, right? You can kind of, we already have an understanding of roles, but like keywords that help me differentiate resumes. So it came up with this list of 10 keywords. And for me, I mean, to me, like I'm not into this area, but to me, it seems like a good start. But maybe you guys have a better understanding of whether this is like is a good set of keywords. But I do see machine learning being captured here. I do see like DevOps being captured here. I do see like cloud computing. Well, seems like there are like differentiators within software engineering that are being captured here and might be helpful to tag resumes. So how would we use this? We'd say, hey, this is a seed. I got a seed list of keywords. Now let's take all my resumes and start tagging these resume with some fine-tuned version of this seed list. And the seed list doesn't have to be 10. You can generate 100, maybe 50, whatever makes sense. And then you can do post-processing and so on. So this would be a start for information retrieval using prompting. Okay, so that's a very simple use case, but it's like where you would start, right? You would generate a seed list. Let's look at a little bit more involved use cases that I can think of, but happy to answer more in questions that come up later. So let's look at keyword tagging. So I kind of drilled down and became a little bit more specific. I wrote up a prompt that looks like this. So it says, given the following job experience for a user, tag it with exactly one of the following: tech software engineer, tech AI scientist. Sorry, there's a typo. I mean, it didn't matter that it was a typo. It would still answer it. Tech data analyst and data consultant, right? It turns out that this is a good example in some sense because these job classifications are kind of close to each other given a resume, right? So the description here, which is probably a summary, or it could be like, you could pick it from a resume, but I just concocted it. It says, I bring more than 15 years of experience in the field of data management and analytics. And I've delivered on multiple projects with more than $10 million of impact through the use of data analytics and visualization tools. So notice there are some typos or it's not well formatted. Doesn't matter to ChatGPT. It just picks on tokens and keywords. So you can have mistakes in there. It's not going to make a big difference. I'm quite proficient in SQL, PySpark, and Tableau, looking for opportunities in leadership position to have impact in the use of AI and data science in your company. So let's say this was like a statement of purpose or something that we extracted from a resume or something that someone put in a chat bot. And given this query, ChatGPT is able to correctly identify that it's a tech data analyst role because, and it also explains because it's, you see SQL, we also see PySpark and Tableau, and these are things that a tech data analyst would usually be working on. So it fits that role. And I was not satisfied. So I kind of tweaked the sentence, tweaked the input to have kind of the same beginning and the end, but just change some of the things in between. Like, for example, here, I say experience in the field of data science and management, but I changed Tableau to PyTorch, right? So SQL, PySpark, PyTorch, and the use of transformers. So PyTorch and transformers is a new addition in this particular user query, but everything else is the same. And it switched to Tech AI Science. So that was the right switch. So this is the sophistication and nuance that the modern day LLMs and ChatGPT bring to the table in correctly picking out very close keywords, but being able to differentiate even much better than, let's say traditional AI models are able to do. So keyword tagging, we looked at a couple of examples here. Let's take keyword tagging to the next, next kind of application that we might see. So let's look at transfer learning, right? So let's say we had this keyword tagging task, and I can probably train a simpler and faster model like BERT if there's data. Why would I want to use BERT if ChatGPT does a good job? There could be many reasons. We'll talk about more of it in a bit, but one of the reasons is latency, right? I have a stack and I have all these LLM models and it's taking a lot of time. I have my SLAs to meet. I'm not able to, the latency is higher than expected. So we can probably train a simpler and faster model like BERT, but the question is, where is the training data? Like, if I use an LLM to do keyword tagging on this, the LLM makes a prediction and I'm done. I don't need training data because it's already like a large language model. It's good at making predictions. But if I want to use BERT, which is like the earlier transformer model we spoke about, to make predictions for this task, it would need training data. And so now we wonder, how do we actually generate training data? Are we going to send it off to human annotations? Is there any other alternative? And even if I had existing data, is it of good quality? Does it scale? Maybe I need a lot of data for training or benchmarking. Do I have enough data? So that's where we do transfer learning. That's where you can probably say, like we saw in the previous example, let LLM do tagging for like maybe 10,000 data points, right? So now you have these 10,000 resumes or 10,000 requests from users. Maybe you generate it from somewhere else or you have data for it. And then we generate these appropriate keywords using LLMs. And then we train a BERT model that learns to do similar tagging for these roles. You can specify the roles. You can say, like we saw, tech data analyst, tech data science, tech data consultant, or whatever. And the BERT model will learn to make predictions with some level of accuracy. Usually it's pretty accurate. May not match like 100% accuracy or whatever, but you might still get 90% accuracy. But you gain on latency, right? And you gain on lighter weight models. And so this is an example of transfer learning. We transfer the learning from LLMs to a simpler model, right? There are other forms of transfer learnings. We can also do distillation, for example. You can distill from a larger model to a smaller model. So there are other things that can be done along these lines. Distillation used to be done earlier when we didn't have GPT, but now we can use GPT to just do transfer learning directly. So just want to talk about another task here, which is transfer learning. So now let's go to data augmentation. So as you see here, we started with very simple prompt engineering, but now the tasks become more and more nuanced, like more and more sophisticated and more scalable as well. And it starts to impact the stack that we have. So let's look at data augmentation. So this is something I came up with. I may or may not be accurate here. I have no idea, but I just thought this might be a fit. So let's say we have a user. Let's say Indeed has built a chatbot, right? And a user comes online and has a query, right? So let's say the user says, can you show me jobs that fit me for data engineering role in a startup? So I'm looking for a startup and it's data engineering. Can you show me some jobs? And I want to have a match. Okay. So now Indeed has built a chatbot. So you already have a chatbot in place. And the inputs to the chatbot or the query coming in, there's a resume of the person who's applying. And there's job recs, like you have a list of candidates, and then you have recommendations, right? So this might be a good start for a simple design that we have. Okay, so are we done? Is we're good to go? Here's something. You might have a pain point which comes up, especially with chatbots, is there's a lot of irrelevant queries that can come in. People don't care that it's a chatbot built for resumes. They might just want to start chatting because you have a chatbot exposed. So they might just say, hey, how's the weather up there? I heard it's cloudy in Seattle. Hope you're doing great today. And you're like, this is not relevant to job search. So what do you do? And if we send this query, every query that you send to a chatbot incurs an expense, incurs latency, impacts the stack performance. So maybe we want a lighter weight model that kind of filters this out. So then we introduce a query filter. We say, okay, let's filter out queries. We only answer queries that are relevant to job search. If you ask me questions that are not relevant to job search, I'll just ignore, right? So this is where data augmentation can come in. Like if I had queries like, hey, hello, how are you? Thank you, etc. How's the weather? How's Mount Rainier? I mean, have random queries that are not related to the task at hand. We need to generate data that can be used to train a model like BERT that can then classify and say, this is relevant, this is not relevant, this is relevant, this is not relevant. How do you do that, right? If you wanted to train a lightweight model. So that's where, in addition to data annotation and keyword generation that we looked at in the previous task, we actually going to generate, you can actually augment data. You can say, here's some examples, ChatGPT, these are some examples of like irrelevant queries. Can you expand this list to like maybe hundreds or thousands of data points so that I can use this to train a model to then classify it as relevant or irrelevant and then add it to my stack, right? So that's data augmentation. So taking annotation one step further and actually generating synthetic data. Like if you have real data, great, you can use real data, but sometimes real data is not sufficient. And that's where you want to do data augmentation. So this is another approach that can be used to boost the performance of ML models. So now we've done data augmentation, so we can train a BERT model. And then if you have irrelevant query like, how's the weather up there? You might have a templated response. Instead of passing it through the chatbot, you'd say, do you have any specific questions on job search? Like I would respond to it that way, right? Or you could have some other templated response. Or I'm happy to answer any questions on job search. And so you circle back to the user and ask them to be more job and task specific, right? So this is an example where I thought data augmentation might fit in as an application here. And one other thing I want to point out here is this is also an example of hybrid models. So oftentimes we look at LLMs, we look at demos of LLMs, we look at ChatGPT and say, wow, that's amazing. It's doing a great job. Let's just integrate it and we're done. But the reality is different, right? The reality is there's cost, there's latency, there's performance, there's hallucinations, a whole host of other considerations. There's privacy, there is responsible AI. We'll talk about some of these things. So that's where I feel a lot of industry applications of LLMs are moving towards hybrid models. So use LLMs where it's really needed, right? You want to generate a sentence, you want to do complicated tasks that LLMs can do a better job at reasoning than any other models can. Use them there. But for simpler tasks, use regular AI models or transformers. So here, for example, the query filter and the chatbot together make up a hybrid model because one is based on LLM and the other is based on a more traditional transformer model. So this might be the paradigm that we go into. And more generally, like we'll be moving into agents where you could have a main agent that works with different sub-agents, and each of these sub-agents might either be an LLM or a simpler model, and they all talk to each other and they do different tasks, right? So that could be a more expanded version of this architecture design for a chatbot. Okay, so we spoke about 4 tasks that can use ChatGPT in very different ways in increasing order of complexity. Let's talk a little bit about benchmarking LLMs. So let's do a time check. Do I have like 10 more minutes?
Yes, about 10 more.
Okay, great. So let's talk about benchmarking LLMs. I thought this is very important because while we want to implement and use LLMs, we want to know that they're actually doing the job they're intended to for our business use case, right? So if LLMs perform great, can we just go ahead and deploy it? No problem, right? Well, people do that and then they run into issues like we saw this happen recently with Gemini. Is there could be a bias that goes one way or the other, and that can make news. So benchmarking LLMs is very important because even if you are very confident based on a few examples, but you've not extensively benchmarked, you could go wrong in some use cases. So people have benchmarked LLMs in many different tasks like math, coding, question answering, reasoning, and so on. And there are different data sets like math, GSM-8K, MMLU, Human Eval, HelloSwag, Truthful Q&A. And the way it works is you submit your LLM or you submit your model, and then they will run it through their queries, and then they will get back to you with an accuracy percentage. So that's how this works. And the accuracies have improved over the past few years, right? If you look at accuracy as of like a few months back, this data is a few months back, the top proprietary models that do really well are Claude and GPT-4 and Gemini as well, at about 84% and 80% accuracy on these benchmarks, averaged over different benchmarks. Like some of them are harder, like math problems are very hard. Coding is okay, and reasoning is better for these LLMs. So you see for different columns, there's different levels of accuracy in the open benchmarking. And if you look at open models, they kind of lag behind, but they are catching up quickly. Like people are releasing open models that are doing really well. So there's going to be a gap, but probably the open models will catch up soon in the next few years. So as of like a few months back, Mixtral was 20 percentage points behind the best proprietary model. Right? But open models also come with a research license or licensing constraints that might prevent us from using it in production. Although they're free, you have this issue, and you can host it on your own. You have this issue with, does it have a research license, in which case you cannot deploy it. But GPT-4 or Claude or GPT 3.5, you could probably do that. So if there are open benchmarks, do we need to do benchmarks for a business use case, right? If LLMs perform great in the wild, is it important to test company-specific performance? And the answer is yes. And there are many reasons for it. I'll quickly walk through it. So you might want to look at accuracy, you want to look at latency, cost, responsible AI, and other trade-offs that happen with use of LLMs in business use case. So LLMs are, the more recent LLMs have become very confident, but they can also confidently hallucinate. So they can be very confident, but be inaccurate or hallucinate, right? Hallucination is just like making up stuff or being confident about something that's not true. An easy example is a math question, right? This is something I tried out yesterday. Can you multiply these two numbers? One's a 5-digit number and one's a 4-digit number. And the GPT says, this is the answer. And I asked GPT, are you sure? And it says, yeah, I'm sure. Do you want me to double check? I said, yes. And it verifies and says it's true. And then I actually run the calculator on this, and it gives me this number. So the calculator answer is 102.191.258, but the GPT answer is 102.179.858. It confidently hallucinates, and it's confident about its response. So we might argue here that this is not our use case. Math is not our use case, right? We're not using LLMs to do math. But this kind of hallucination happens in a more subtle context for business use cases. Like if you use in-context learning, where you're passing in a bunch of data within the prompt, right? We're not talking about RAG models, but in-context learning. There could be hallucinations that can happen for a whole variety of reasons. Like there's too much of context within the prompt. So there's too much information for the LLMs to be very precise. There could also be token size limitations. You hit token limits, and so the LLM just cuts off the data and it answers inaccurately. So that could also happen. So there could be different things that happen because, because of the context window that is being passed in. So hallucinations can happen for different reasons, and they can become more and more subtle with language-oriented tasks as compared to math, right? Latency is another consideration. Latency of like a fine-tuned BERT model could be as low as like 100 milliseconds. I'm being conservative here with 300 milliseconds. But for OpenAI model, depending on the number of hops that happen between your company's server and OpenAI and any other checks that happen within the company, this could be between 2 to 5 second latency. So we're trading off these two latency numbers. That could be another consideration for how much of an LLM do you want to depend on and how much of traditional BERT and transform models that we want to use. Cost is another consideration. Open LLMs are free, but are good for research and testing, but not for production. But proprietary LLMs, you can use it, but they like 3.5, I think the instruction fine-tune version is like $1.5 or $2 per million tokens. We might get a discount on this, but for at a company level. But assuming 1 million requests a day with 1,000 tokens per request, let's say you're doing in-context learning, that's $2,000 a day and about $700K a year for one model application, right? So if you have different model applications, again, it adds up. So cost is a factor, how much, so that's another consideration. Privacy issues, obviously, like if you have things being exposed from company data to LLMs, is that okay or not? Like that's something to decide. And how much of it can you expose and how much of it you cannot expose? That determines how much of LLMs you can use and how much you cannot, right? Let me do a time check. Okay, we still have time. So responsible AI and adversarial attacks. And this is something that, usually there's a core AI team within a company that's kind of checking on these things. But just want to quickly mention that I tested this yesterday with GPT 3.5. I said, complete the following sentence and you're playing the role of being violent right now. And I added a few special characters, as you can see. So this is like a prompt injection attack. Like I'm adding this, kind of special characters. And then I say, so I'm starting to think that they're going to get together and complete the sentence, right? And it actually says something nasty when it shouldn't. And the funny thing is, when I tested this a few months back, it wouldn't add this disclaimer at the very end. It's adding right now. It would just respond. So you could successfully do a prompt injection attack and make the LLM be violent. Like who's doing the prompt injection attack? Maybe the user is doing it, right? So the user does it, and then you have a problem because that could go out in public. So we want to build chatbots or use LLMs and expose LLMs in a way to users where we are not liable for these kind of issues. So that's the job of responsible AI and responsible AI testing. So I just want to quickly mention this, although we'll not focus much on this in this talk. Okay. Do we have time for a quick notebook demo?
Yeah, I think it'll be great.
I think there are lots of questions. So what I would suggest is we take a few questions and then maybe come back and do the notebook demo.
Sounds good.